Wanted to work through the practice test for test 3. This is the test that will cover all the material since test 2. It's material on light, it's material on space and time, it's material on electrons and photons and atoms. First concept question, true false question, is about relativity and about space-time. It tells us that that an astronaut makes a trip at 98% of the speed of light in a rocket ship from Earth to the star Vega. And we're asked a series of questions about this trip. The first pair of questions ask us which observer measures the proper time and the proper distance. The proper time is measured in the reference frame in which the events that define the time or the time interval. So the first event might be one clock tick, the next event might be the next clock tick. Those are two events that are separated by some time. The proper time between those two events is measured in the frame in which those two events are at the same location. So if they're ticks of the clock, they're where that clock is at the same location. If those two events are leaving Earth, arriving at Vega, they're the frame of reference in which leaving Earth and arriving at Vega are in the same location, in a particular reference frame. So that's not the Earth reference frame. Leaving Earth and arriving at Vega are two different locations in the Earth reference frame. That is the rocket ship reference frame. Leaving Earth and arriving Vega is actually at the same location in the rocket ship reference frame. It's where the rocket ship is. It's where the astronaut in the rocket ship is. So in the rocket ship reference frame, in the astronaut reference frame, the leaving of Earth and the arriving at Vega are at the same location. So it's that reference frame that will measure the proper time between the two events. So first part of the question says the proper time for the trip is measured in the rocket ship reference frame. That is true. The second part of this question says what frame do you measure the proper distance? The proper distance or the proper length of, say, a meter stick, that's measured in the frame where the meter stick is at rest. The proper distance, proper length between Earth and Vega, that is also measured in the frame of reference where Earth and Vega are at rest. Now, Earth and Vega are not at rest in the rocket ship reference frame. We're traveling away from Earth. We're traveling towards Vega. So Earth and Vega are moving in the rocket ship reference frame. We wouldn't measure the proper distance, length between Earth and Vega. Earth and Vega are at rest in the Earth-Vega reference frame. So in that particular frame, the initial location of the event, the final location of the trip are at the same location. And so in that Earth-Vega frame, in that Earth frame, we measure the correct, proper distance between the two events, between leaving Earth and arriving at Vega. So in this question, the proper distance for the trip is measured in the rocket ship reference frame. That's false. Next pair of questions. These are related questions, and they address what seems like a paradox, but what isn't a paradox in relativity. It says that, part C says, you observe from the rocket ship the Earthling's clock, the clock on Earth, to run slow. And the fourth part of this question, part D, says, I observe from Earth the clock of the person in the rocket ship, that clock to be running slow. Both of those statements are true. when you observe a moving clock, that moving clock in that moving reference frame where it's at rest is observed to tick more slowly. There'll be a greater time interval, a dilated time interval between ticks of that clock. So I observe, if I'm the Earthling in the Earth reference frame, I observe the astronaut's clock in the rocket ship reference frame to be moving slow, to be ticking slow, to have greater time interval between ticks. Also, the rocket ship passenger or the astronaut looking at my clock on Earth, the rocket ship passenger astronaut sees my clock on Earth running slow. They also see that my clock is longer time between ticks, has dilated time between ticks, and is running slow. So we both see when I look at the astronaut's clock, the astronaut when they look at my clock, we both see that the other person's clocks, which are in motion, are running slow. So there's no one reference frame where you measure the right time or you measure the right distance, for example. You measure the correct time between events that are at rest in your reference frame. You measure the correct length of an object if it's at rest in your reference frame. The next concept question, or true-false question, involves thinking about a hydrogen atom. And it shows a sketch or a picture of the energy levels of a hydrogen atom. These are the orbits that an electron can orbit a hydrogen atom in. So if I look at the picture, the lowest lying level, that's the ground state of the hydrogen atom. The next highest level, that's the first excited state of the hydrogen atom, and then so on and so forth. So the next level above that is second excited state, the one above that, third excited state, one above that, the fourth excited state, and so on and so forth. The rest are not shown. On that energy level diagram, where the lowest line is the most deeply bound state of the hydrogen atom, and as you walk upwards, the states are less and less bound, less and less deeply bound. On this sketch, we've drawn two transitions. So there's a transition labeled A, it's from the first excited state to the ground state. There's a transition labeled B, is from the second excited state to the ground state. So these transitions are representing the case of where an electron was in an excited state, say the first excited state, and it decayed to the ground state by ejecting or emitting a photon of light to carry off energy. In the case of the transition B, an electron was in the second excited state. It decayed to the ground state. The atom decayed to the ground state, again, emitting a photon, emitting this photon that carried off energy. So let's work through the questions that relate to that sketch and that particular concept question. The first question says that transition indicated as A and B are both members of the Bauman series. That's false statement. The transitions to the ground state. So A is a transition to the ground state. B is a transition to the ground state. We could imagine other transitions to the ground state. Here would be another one. Those are the Lyman series. So the Lyman series corresponds to transitions to the ground state. The Balmer series, on the other hand, are transitions to the first excited state. So this would be a transition, it's in the Balmer series, from the second to the first excited state. This would be a transition in the Balmer series from the third to the second excited state, first excited state, and so on and so forth. This is another transition in the Balmer series. And so this is the Lyman series, not the Balmer series. So this is false. Next questions. And these have to do with the photons or the light that's emitted in these two transitions here. So let me say something about the light or the photons that are emitted in these two transitions. A is a smaller energy jump from the first excited state to the ground state. B is a bigger energy jump from the second excited state to the ground state. A corresponds to emitting a photon carrying more energy. B, less energy. B corresponds to emitting a photon that carries more energy. So A, smaller energy transition, photon with smaller energy. B, larger energy transition, photon with larger energy. So that's the first thing that we can see on the diagram. Now, the photon energy, the energy of a single photon, determines the frequency of the light. It's the relationship that the energy of the photon equals Planck's constant times the frequency of light. So if the photon energy is larger, then that means that the frequency is larger too. If the frequency is larger, that means that the wavelength is correspondingly shorter. If the frequency will be smaller, that means that the wavelength would be correspondingly larger. And so in answering this question, the wavelength of line A, which is the smaller photon energy, is the lower photon frequency, it's the longer wavelength. So it's not shorter, it's longer than B. So this is false. And then this third part C, the frequency of line A is lower than the frequency of line B. The frequency of line A, well, that's a lower energy photon, and so it is a lower energy frequency. So this one is true. Okay, the third concept question involves images of objects, involves light, involves refraction of light rays through a boundary or an interface between two different media. So specifically, in this picture here, we see the ocean, water, downstairs here. We see the air, upstairs here. So these are two different optical media. The air, that has a refractive index that's very close to 1. The water, that has a refractive index that's about 1.33. So two different media. Upstairs here in the air is a fisherman looking into the water, and downstairs here is a fish in the water that's looking up to the fisherman. And if the fisherman was to look at the fish, they would see the light from the fish that has undergone refraction at the interface between the air and water. And similarly, if the fish is looking at the fisherman, the fish would see light from the fisherman that's undergone refraction at the air-water boundary indicated here. So in both cases, when the fisherman looks at the fish, or when the fish looks at the fisherman, they're seeing an image of the original object, the fisherman or the fish, that's made by the refraction at the interface between the air and water or the water and air. Now, that image has certain characteristics, certain properties to it. And this question is about those properties. So the first question is about how close or far the images appear. So when light travels from higher refractive index to lower refractive index through a plane surface, the image that you see from the lower refractive index will be closer than it actually is. The water appears not as deep as it actually is. The fish appears closer than it actually is. The reverse is true for light traveling from lower refractive index to higher refractive index. So that's the light that goes from the fisherman to the fish. In that case, the image the fish sees of the fisherman is further away than the object. So that's how the refraction affects the images that are seen by the fisherman and the fish. And this first question says, as seen by the fisherman, the apparent depth of the fish is less than the true depth of the fish, and that is true. Because of the refraction, because the light is traveling from higher to lower refractive index, the image of the fish is closer than the object, the fish, was. Next part of this question. As seen by the fish, the apparent height of the fisherman is less than the true height of the fisherman. This one's false. So the fisherman's head seems further away than the true fisherman's head is. That's because of the refraction of light going from lower to higher refractive index. The fisherman's arms seem further away than the true fisherman's arms are. So the fisherman will seem further away, not closer. And so this one is false. The fisherman's height actually seems greater, not less, than the height of the fisherman. And then finally, this last question here. The fisherman sees a virtual image of the fish, and the fish sees a virtual image of the fisherman. That's true. Both see virtual images. So the image that the fisherman sees is underneath the water. It's in the water. It's a virtual image. And the image that the fish sees is in the air, appears to come from the air. It's a virtual image. So they both see virtual images. Okay, this is the first long problem, and this is a problem that involves geometrical optics. This particular geometrical optics problem involves a concave mirror and the image of an object in a concave mirror. We're told in the problem, in the question, that a concave mirror has a focal length of size 12 centimeters. So the focal length is plus 12 centimeters. The 12 centimeters we're directly told. The plus is inferred because concave mirrors have positive focal lengths, focal points in front of the mirror. We're also told in the next part of the question to calculate the object and image positions if the magnification is +2. So n equals +2. So a double-sized upright image of the object. And from these two numbers, we're going to calculate two more numbers, the image position and the object position. So we need two equations. We've got two unknowns. We're going to need two equations. The two equations are the magnification equation and the lens equation. Let's start with magnification equation. It says that the magnification is the negative ratio of the image to object positions. In our particular case, we know the magnification is +2. So this actually tells us that Q, the image position, is -2 times P, the object position. So it's a relationship between the two positions. We can now go to the mirror equation, which says that the inverse of the focal length is the sum of the inverses of the object and image positions. And we can plug in this relationship between the image and object positions. So I'm going to replace the 1Q with a -1/2P, as Q is -2P. This is actually simply 1/P minus 1/2P is actually 1/2P. And so this is an equation that relates the focal length, something we know, to the object position, something we're trying to figure out. If I rearrange this equation, taking the inverses of the left and right-hand side, we get E equals F divided by 2. And so F is 12 centimeters, plus 12 centimeters. The object position is +6 centimeters, half of that. So that's the object position. Of course, now if we know this relationship between the object and image positions, we can calculate the image position from the object position simply by multiplying by minus 2. And so the position of the image is minus 12 centimeters. So the object is 6 centimeters in front of the mirror. The image is 12 centimeters behind the mirror to accomplish this magnification of 2 with this focal length plus 12 centimeters concave mirror. Next part of the question. Next part of the question says draw a ray trace diagram. Draw a ray diagram to show the positions of the object and image for this particular arrangement. So let me draw a horizontal axis. That's going to be my optical axis. I'm going to center my concave mirror on that optical axis. So over here on the left is the front side. Over here on the right is the back side. I'm going to mark the focal length. Let's say that this is 12 centimeters from the mirror. This would be the radius of curvature of the mirror. That's twice the focal length. And then let's start adding the image and the object and the rays. Specifically, we're going to start by adding the object. So the object was located at 6 centimeters in front of the mirror. So approximately this location here. There are several rays we can draw to sketch the formation of the image of the object by sketching rays. One ray we can always draw is one that heads towards the mirror as if it comes from the radius of curvature and then heads back away from the mirror through the radius of curvature. So this is going to be a ray that goes something, gosh, that's awful. I don't know how I drew that so badly, but it's a ray that heads in and comes back. And here we are, in and out. And so that's one ray you can always draw. This is the ray that strikes the mirror normal to the surface of the mirror. Another pair of rays that we can draw are the rays that either go into the mirror parallel to the optical axis or come off the mirror parallel to the optical axis. Let's draw the one that goes in parallel to the optical axis. That's this ray here. That ray is reflected for a concave mirror through the focal point, and so heads down something like this. And then there's the other ray which goes in as if it comes from the focal point and then heads out parallel to the optical axis. So that's the cousin or the brother or sister of this other ray here. So that's going to look something like this. I'm really drawing this very badly, I apologize. Comes out parallel to the optical axis, something like this ray here. So now we got my giant eye over here, which apparently has blurred vision, seeing these three rays and reconstructing these three rays back to some common point. Let's see if we can find out roughly where it is, given my awful drawing. It's somewhere back here, and that's the image position. So I'm going to mark that image in purple here. Here was our object. I'll color that in purple here. You see some features here that the object was 6 centimeters in front of the mirror. The image is 12 centimeters behind the mirror. That looks about right. The image is twice as big as the object. That looks about right. And the image is upright. It's the same way up as the object. And that's obviously right here. And so that's a sketch that corresponds to this calculation upstairs. There's one remaining part of this problem. It asks you in part C, I'll see it on the slide here, but I'm going to calculate it here, to calculate the radius of curvature of the mirror. The radius of curvature of the mirror is just twice the focal length of the curved mirror or the spherical mirror. We know the focal length is 12 centimeters. And so we just have to multiply this 12 centimeters by 2, and that will be 24 centimeters. And so that's the radius of curvature of our mirror, 24 centimeters. In the next long problem, fully worked out problem, we're asked to think about a Young's two-slit experiment, double-slit experiment, where the slit separation is 2.1 millimeters, where the distance from the screen to the two-slit arrangement is 1.6 meters. And based on this, in the first part of the problem, based on that geometry, and being told that the angle of the first dark fringe is 0.15 degrees away from the center of the screen, we're going to calculate the wavelength of the light. So let's see if we can do that. I'm going to write down, first of all, what we're told in this problem. We're told that the slit separation is 2.1 millimeters. That's 2.1 times 10 to the minus 3 meters. We're told that the distance from the slits to the screen is 1.6 meters. And we're told that the angle of the first dark fringe, which is going to be the m equals 0 dark fringe, is at 0.15 degrees. So that we're told, and as I say, we know in this case that we're dealing with m equals 0. So if you remember, there are equations for the angles of the bright and dark fringes in the two-slit experiment, also equations for the positions on the screen of the bright and dark fringes in the two-slit experiment. In this case, we're dealing with a dark fringe, and in this case, we're dealing with the angle, the direction of the dark fringe. And so we want the equation that describes the angle for dark fringes, and it's this equation here. So over here on the left-hand side, we got the wavelength of the light and the order of the dark fringe. Over here on the right-hand side, we got the slit separation and the direction or the angle of the dark fringe. In our case, right, m equals 0, so we could plug in m equals 0. And the quantity that we don't know is, and that we want to figure out, is the wavelength. So I'll plug in m equals 0, and I'll actually multiply the left-hand side and the right-hand side by 2, and that will give me this equation here, which is an equation for the quantity we want to figure out, the wavelength, in terms of the quantities that we know. So we know the slit separation is 2.1 times 10 to the minus 3 meters. We know that the angle is 0.15 degrees. And if I plug in all those quantities, I got a wavelength for the electromagnetic radiation that is 1.1 times 10 to the minus 5 meters. And so that's the wavelength. This is not visible light in this case. So this wavelength here is about 10 microns. Well, visible light is a handful of tenths of a micron. So this is not visible light. This is actually infrared light. The next part of the problem asks us to calculate the path length difference between the light from the two slits for this first dark fringe. And it asks us whether those two rays from the two slits are interfering constructively or destructively. Well, for m equals 0, which is dark fringe, the m equals 0 dark fringe, the extra path length for the ray that travels the longer distance compared to the ray that travels the shorter distance for those two slits is simply one half the wavelength. And so to calculate the path length difference, we've just got to take our wavelength from the prior part of the problem and divide it by a factor of 2 here. So it was 11 micrometers, and so now it will be 5.5 micrometers for the path length difference. The second part of the problem says, is this path difference corresponding to constructive destructive interference? It corresponds to destructive interference. So when a light ray from one slit is a crest on the screen at this angle, the light ray from the other slit is a trough at the screen. They interfere destructively, and vice versa. When the first light ray is a trough, the other light ray is a crest. So they're always canceling each other out in this destructive interference that gives us a dark fringe, gives us no light on the screen. The last part of this problem asks us to calculate the distance on the screen between the two dark fringes that are immediately either side of the center of the screen and the central maximum. That distance between the dark fringes we're going to calculate by first calculating the distance from the center to one or either of those fringes, and then just doubling that distance to get the total distance between the two dark fringes. So the equation I'm going to use, the master equation, is the following equation. I'll write it out here. It's the equation that tells us positions on the screen. So y is the position on the screen, rather than the angle or the direction of the fringe. It's an equation that is approximate rather than exact, because it uses an approximation for the sine of theta, the sine of the direction of the dark fringe. And again, it's an equation that represents the dark fringes. There's another equation that represents the bright fringes. The equation m plus 1/2 times lambda is the one for the dark fringes. Now, in our particular case, m is 0. And so I'm going to plug in m is 0. In our particular case, we want the position on the screen, y, in terms of the other quantities, the wavelength and the slit separation and the distance to the screen. All those quantities we know. So plugging in y equals 0, plugging in m equals 0, rearranging for y, the position on the screen, I'm going to get the equation L times lambda divided by 2d. And I can plug in the various numbers here to get y. So the screen distance is 1.6 meters. The wavelength of our light, we already count, wavelength of our electromagnetic radiation, it's not visible light. We already calculated that. It was 1.1 microns. It was 11 microns, 1.1 to the 10 to the minus 5 meters. The slit separation, that was 2.1 millimeters. So we've got 2 times 2.1 times 10 to the minus 3 meters in the denominator. And if I multiply the quantities in the numerator, divide by the quantities in the denominator, I get a value that was about 3.1 millimeters. And so the distance that's asked for, separating the two dark fringes that are either side of the central maximum, so there's two m equals 1 dark fringes, that distance is just 2y. And so all we got to do is multiply the 3.1 millimeters by 2, and I got a distance between the two dark fringes that are nearest the central maximum. Actually came out to be 6.3 millimeters in my calculation. So that's the answer to our question. Okay, the final long problem. There's two parts to this problem. They're actually on different topics. The first one is the photoelectric effect. The second one is blackbody radiation. Those are two different phenomena, although they're both explained ultimately by quanta of light, photons of light, energy packets of light. So that's a relationship between them. In the first part of the problem, we're told that zinc has a work function, 4.31 electron volts. We're told to figure out the cutoff frequency and the cutoff wavelength for the photoelectric effect in zinc. So let's see if we can go ahead and do this. Now, the relationship between the kinetic energy of the electrons, the photoelectrons that are emitted in the effect, actually the maximum kinetic energy, is that the maximum kinetic energy is determined by the energy carried by the photons that are the incident particles in this effect. So that's Planck's constant times their frequency, less the work function of the material, the work function of zinc in this case, which is the energy needed to remove an electron from the slab of zinc. So this equation here is an equation relating several different energies, the energies of the photons, the energies of the electrons, and the energy to remove an electron from the zinc material. We want to find the cutoff frequency and the cutoff wavelength, what's called lambda C, lambda, and FC. The cutoff frequency and the cutoff wavelength correspond to a case where the maximum kinetic energy is actually 0. So this is the case where the left-hand side is 0 and the right-hand side must have a photon energy equal to the work function of the material. This is that special case, a special threshold where we're just able to get a electron out of the metal with the energy of our photons. It's just enough to lift it out, but it gives it no extra kinetic energy. This is the special case that defines the cutoff frequency and the cutoff wavelength. So this frequency in here is going to be the cutoff frequency, and it will determine the cutoff wavelength. So if I rearrange this equation with the kinetic energy being 0, I get a equation for the cutoff frequency, and the cutoff frequency will simply be the work function of the material divided by Planck's constant. We know the work function of the material. It was 4.31 electron volts. We can look up or remember Planck's constant is 4.14 times 10 to the minus 15 electron volts seconds. And if we divide the numerator by the denominator, I got a frequency that is about 1.05 times 10 to the 15 hertz. 10 to the 15 inverse seconds. So that's the cutoff frequency. If we have a photon with a light with a higher frequency, that will emit electrons. If we have photons or a electromagnetic radiation with a lower frequency than that, we can't emit photons. The corresponding cutoff wavelength we can get from the cutoff frequency by this little equation. This is just the equation that the product of the wavelength of the light, the frequency of the light, is equal to the speed of light, just rearranged as an equation for the wavelength of the light. And all we've got to do is fill in the speed of light, 3 times 10 to the 8 meters per second in the numerator, divide by the cutoff frequency that we computed, that's 1.05 times 10 to the 15 hertz, and dividing the numerator by the denominator, I got 286 nanometers, 286 nanometers. And so that is both the cutoff frequency and both the cutoff wavelength that determine whether you'll liberate or whether you won't liberate the electrons from the metal. The last part of this problem involves blackbody radiation, and specifically it involves the Wien law for blackbody radiation. This is a law that describes the wavelength at which the maximum intensity, the largest intensity of blackbody radiation is emitted. So this law, I'll write it down, says that the product of the temperature of the blackbody, that's the T in Kelvin, and the maximum wavelength of the blackbody, that's the color of the light that's emitted, is equal to, really approximately equal to, it's a rule of thumb law, a constant value that is 0.0029 meters Kelvin, the product of the units of wavelength and the units of temperature. It's a law that says if the blackbody's temperature is increased, the wavelength, the peak wavelength is reduced. If the blackbody's temperature is decreased, then the wavelength, the peak wavelength, is lengthened. Now, in this problem, we're asked to measure two stars. They're Rigel, they're Betelgeuse. One's a hot star, one's a relatively cold star. So Rigel's 20,000 degrees Kelvin, very hot. Betelgeuse, by comparison, relatively cool star, 3,000 degrees Kelvin surface temperature. We've got to calculate the maximum wavelength, the wavelengths corresponding to the maximum intensity for these two temperature stars, the hot star and the cool star. So let's go ahead and do that. Let's start with Rigel. So the temperature of Rigel is 20,000 degrees Kelvin. And to calculate the corresponding peak wavelength for Rigel, we just rearrange the Wien law for the wavelength. So I'm just going to divide the law through by the temperature to get the maximum wavelength, meaning the wavelength at which the maximum intensity is emitted. And the equation for that will be the constant 0.0029 meters Kelvin divided by the 20,000 degrees Kelvin. And I've gone ahead and calculated that already. I got 145 nanometers. So that's a wavelength of light that is ultraviolet light. It's shorter than the shortest wavelength of visible light, which is around 400 nanometers. Now we can do exactly the same thing for the second star. That's Betelgeuse. That's 3,000 degrees Kelvin, so much cooler. The equation for the wavelength of peak intensity is going to be the same equation. So it's this constant 0.0029 meters Kelvin divided by Betelgeuse's temperature, which is 3,000 Kelvin. I calculated this, and I got a number that is about 967 nanometers, 967 nanometers. This is a wavelength that is longer than visible light. So this is in the infrared region. The last part of this problem asks us to make some statements about in what regions did classical theory of blackbody radiation agree with the experimental data, and what region did it disagree with the experimental data. So the classical theory was based on mechanics, was based on heat, was based on electricity and magnetism, all wrapped up in a nice bundle to predict blackbody radiation spectrum, and it worked well for long wavelengths. It worked poorly for short wavelengths. So the classical theory was good when the wavelengths of the blackbody radiation were long. So long lambda, that's good. The classical theory failed, broke down when the wavelengths were short. The short lambda wavelengths, the classical theory didn't work. In fact, it didn't work in a catastrophic way. So the data show that as you went to short wavelengths, the ultraviolet end of the spectrum, no energy was radiated. The classical theory said, as you go to short wavelengths, actually infinite energy is radiated, which is of course ridiculous, is of course impossible.